everyone, welcome to Gemchem. Now today's video is on Coordination Chemistry Part 2 video, and here we are going to deal with more bidentate ligands example along with other denticities. Now in the previous video we have already dealt with two different bidentate ligands. One was ethylene diamine and another was oxalato. Today we are going to start with more examples. So before starting, if you are new to Gemchem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So in this case today we will see acetyl acetone. This looks like somewhat this. Here we have C double bond O and here we have C double bond O. So this carbon actually contains hydrogen in it. So one of the hydrogens, if we place it like this, what happens is that this hydrogen is given up and this oxygen opens up. Finally we get acetyl acetonate O. This is a enol form of this acetone. So we have double bond here and this one, this opens up, so O minus, we have double bond here and the metal binds with this oxygen. One of the examples of such a complex, if we do, we can take Mn3 plus and the complex will be Mn AC AC. Acetyl acetone is being represented as AC AC 3. Since this is bidentate, we will have 3 of them to complete the octahedral geometry. Now let us see the next one. Next one ligand will be our dimethyl glyoxal. Dimethyl glyoxal. It looks like CH3 double bond O double bond on, and to it when we add 2 NH2OH, what we get is same thing, but here there is attachment of NOH and here also NOH. And if you look here carefully, this is known as dimethyl glyoxide, which acts as a ligand part. How does it act as a ligand part? One of the hydrogens present here is given up to the oxygen and oxygen gains a minus charge. Similarly, in the other case, we have another ligand which does so. Finally, what we get is like this, double bond N, N, here we have OH, here we have N and O minus. So this is our DMG, right? So this DMG will make complex with nickel to form nickel DMG 2, and this complex formation we will see in the next page. If you consider the nickel in between, we have one of the centers as nitrogen, another one as nitrogen. Similarly for this one, nitrogen and nitrogen. This nitrogen has O minus, this nitrogen has OH. Similarly, this will have alternately OH and this will have O minus. And join these with the normal bonds. Similarly for this side, we are going to do the same thing. And finally, there will be a hydrogen bonding between this one as well as this one. So this is nickel DMG complex. And this is actually NiH-DMG, where there is presence of one hydrogen atom in each ligand, which is this one and this one respectively. Now, if you remove these hydrogens also, there will be no hydrogen bonding. Finally, what we get is nickel DMG complex only, DMG 2 minus, right? And here you have to remember that this particular complex which we had already drawn here has an importance, because when we detect nickel during our practicals, we get a rose red precipitate during the test. So this rose red precipitate is due to this formation of complex, right? Now here the stability comes from the hydrogen bonding, as well as there is a negative charge density not localized over carbon but over oxygen, which is itself a electronegative part. Now we will shift for our next bidentate ligand, which is biguanide. So here biguanide looks somewhat like we have a nitrogen center in between. In the two sides we have 2 NH2s and we have in between double bond NH. Similarly in this side we have double bond NH and here we have a hydrogen. This is known as biguanide and it has short form as H big. Now if you remove the hydrogen present here, then what happens is that we get another one which is big, that is biguanide without an H. So let us start drawing that. If it loses one H plus, it becomes N minus, and here we have double bond NH, NH2, and here also we have double bond NH and NH2. Here you can see that this minus can migrate or resonate to form more stable structures, and here we have a metal attached to the two nitrogens. An example of such a complex is Cu big 2 whole. This is a complex. Now if you try to draw this complex, how to draw it? Let us see. Put the copper within the middle portion. Then you have to draw the nitrogens in the four sides. This is a 4 coordinated complex. Here we have double bond, here we have double bond. Attach it with a nitrogen in between and NH2 on the two sides. The nitrogen has a negative sign. Similarly, here also you will do the same, N minus, and here we have NH2. In this side we have NH2. This is negative and the copper is actually 2 plus. Here we have NH, NH, NH and NH. This was our next one. Now we will see bipyridine, orthophenanthrolene and phenylazopyridine. So these ligands look like somewhat this. This is our one benzene ring attached to another benzene ring. Now what you have to do is remove one of the carbons from each. So remove this and write this as here nitrogen. Here also we have a nitrogen, then join it. This is known as bipyridine. And the short form is BPY. The complex looks like FeBpY3 2 plus, and the iron has also 2 plus charge. Next we will see orthophenanthrolene. So if you draw it, first you need to know the phenanthrene structure, which looks like somewhat this. Now remove 2 of the carbons and replace it with nitrogen. So here we will put a nitrogen, then join. Here we are going to put a nitrogen and then join. This is orthophenanthrolene. This is also bidentate ligand where bonding occurs with the help of the two nitrogen present. One of the examples of this complex is CO, that is cobalt, 2 phen whole twice Cl2. It has short form as PHEN. Next ligand which we will talk about is phenylazopyridine. So from the word only you will have an idea that we will have a phenyl ring, this one, then we will have a azo bond, then we will have a pyridine. Now what is pyridine? We already know. If you are unaware of that, you can watch it. I will give the link of the video in the description box as well as the I button present above this video. Now see here, we will replace it and place here nitrogen and then join the bond. So the bonding will occur from the two nitrogen centers, that is this one and this one. This is a example of redox non-innocent ligand. Just know about this. This will be discussed in the later videos. And since it is known as phenylazopyridine, it is written as PAP. So cobalt 3 PAP twice Cl2 plus. Another ligand which we will talk about right now is the other type, which is tridentate ligand. Now in this tridentate ligand, from here only you can understand, then there will be 3 donor centers. The simplest of the tridentate ligand is our diethyl triamine. Diethyl triamine, and it has a short form of diene. This will look like NH2 join with CH2 CH2 NH, again join with CH2 CH2 NH2, and the bonding will occur from these 3 nitrogen centers with a particular metal. An example of this one is CO diene twice 3 plus, and here is 3. So diene 2 means there will be coordination number equal to 6. Try to draw it, put the cobalt in between, then place the 6 hands of it, then write NH2, NH, then NH2. Similarly, in the same way, here write NH2, here write NH, and here write NH2. Finally, draw their CH2 part, CH2, CH2. Similarly for this one, CH2 and CH2. So from here you can see that there is a formation of octahedral complex, right? Next ligand which we will talk about in tridentate ligand will be thiopap, substituted pap. So in this case we have same a phenyl ring, but in the phenyl ring we will have a SH group. Similarly we have a azo bond, and from azo bond we are going to have a pyridine, right? Now the bonding will take place from nitrogen, from this azo bond nitrogen, and from this sulfur. This is known as thiopap. Next one will be our pyridine 2,6 dicarboxylic acid. So write down pyridine 2,6 dicarboxylic acid. So first draw pyridine. This is our pyridine, done. Then on the both sides of the nitrogen draw acid group. This is easy, right? So acid group is being drawn. Now the donor centers will be oxygen. 2 oxygens will be our donor center, and nitrogen will be our donor center, and here will be our metal, right? Now we are going to deal with the next type of ligand, which is known as flexidentate ligand. So there are some ligands which can donate electron density through all possible donor centers or through some of them under different experimental conditions. This phenomena we refer generally to as flexidentate nature of the polydentate ligand, and such ligands are often referred to as flexidentate ligand. So let us see an example. Pyridyl azo-oxime. Pyridyl azo-oxime. So first we have a carbon, azo-oxime NOH, and we have a aryl group, same azo bond. Then we will have a pyridine. Here we have a nitrogen. This will be joined together to form a pyridine. This is done. So this is our pyridyl azo-oxime. And if we try to show the bonding, in general it can be tridentate as well as bidentate. When this OH is present here in the same side, nitrogen from this azo bond comes, pyridine bond comes, and from oxygen comes to form tridentate ligand. But when the OH is present on the different side, then what happens is that here if the OH is placed in the opposite side, in that case bonding only occurs from this nitrogen and the pyridine nitrogen. So from tridentate it becomes bidentate. Now we will see tetradentate example. Tetradentate example means that there will be 4 bonding centers, and previously we have seen N, diene, now we will see triene. It means that it is triethylene tetraamine. So draw NH2, CH2CH2NH. Similarly write CH2CH2NH, and we have CH2CH2NH2. If you place a metal in between like this, there will be bonding from the 4 centers of the nitrogen to the metal, right? So the metal in between, and we have 4 nitrogens on the 4 sides, thus making it tetradentate ligand. And always write the hydrogens present with the nitrogens. If you miss it, the complex gets wrong. The last one which we are going to deal with is hexadentate ligand, and this is very important. One of the example of it is ethylene diamine tetraacetate. This particular chemical is used in laboratory to do particular titrations which are known as complexometric titration, as well as it helps us to understand the hardness present in the water using the chemical. So first example which is very important is we have ethylene diamine tetraacetate, right? So here we have nitrogen, and here we have the other bondings, C double bond O, OH. Similarly here we have O, OH, double bond O, OH, double bond O, OH. Okay, there is one carbon which will be present here. Here there will be no double bond. The next carbon will have the double bond, right? So here we can count the 6 centers. One is this oxygen, one is this nitrogen, oxygen, 4, 5 and 6. These are the donor centers. Here we write it in short EDTA. Now the titration and the basic principles regarding the complexometric titration using this EDTA will be discussed in the next video. So here ends the types of ligands which we have already dealt with. In the next video we are going to deal with chelation and chelate effect and macrocyclic ligand and its effect. So this much for today. Thank you for watching. Do not forget to like, share, subscribe and comment.